All right. Let's see here. Okay, so this is how I'm going to do this. I am going to pull up the past paper, the specific questions that we'll be working on. And then I guess, how would I see? Okay, I'm just going to work through it. And then I'll just check the chat occasionally to see if there are any questions. But I'm gonna work through two past papers right now, and those are specifically under the broad topic energetics. I realized I didn't really have any videos on that, didn't really emphasize that in all of the sessions that I did. But you see how nicely mole concept fits in, usually at the end of these questions. So I'm gonna do that, and you'll see that once you kind of get the hang of it, you kind of have it, right? So I am going to pull up the past paper. So let me just share that from my meeting that I'm in. I really should have maybe sent out this Zoom link so you could interact here if you wanted. Let me see. Maybe I will do that too, just in case. So let's see. I'm gonna send it and see. Give me a minute here. I'm gonna copy this part. And then put it on my story. So for those of you who are joining me from the Instagram, you'll be able to join very quickly. So I'm just gonna do that real quick. This is a very impromptu pop-up session, right? I didn't really expect to be here tonight because I don't want you guys to freak out. But I figured I would make this video and it would be there if anybody really feels as though they're lost on this energetic stuff when it comes to solving these problems. So I'm gonna just pop this on my story so that those of you who want to join via the Zoom meeting can join there. So you can interact with me there if you want to, right? It's only if you want to. It's no pressure, but I'm gonna send that. So I'm gonna send that link right now. So just give me a minute. And then you'll be able to join a Zoom meeting if you want, right? We're not intending on this being a long meeting. It's just a quick problem solving session, but I wanted to give you guys this, show you guys how this works if you wanted to see it. So let's see. I'm gonna just share the link on Instagram for a Zoom meeting so you can join. So let me just write this real quick. Join us on Zoom using this link. And then I'm gonna put the link right beneath it. So you can pop in on Zoom if you want. Zoom meeting link. All right, so I have that up on a Zoom meeting link now up on the Instagram story if you wanted. And then perhaps what I will do is I will put it in the YouTube chat as well, which it probably wouldn't need to. It's kind of redundant for you guys who are already on YouTube. But let's put it in anyways. So here it is. All right. Okay, so I just did that. So what I'm gonna do now is I'm gonna share my screen from Zoom. Okay, so let's start with, which one did you want to start with? Let's start with the January 2011 So I'm just going to share that, and I'm already there. You can see that. Okay. So here we are. Actually. Okay, so here we are. Okay, here we are. So we are back. Okay. So this is the first question that we'll do on the energetics. So this is from January 2011. So I had to go way back in the past papers to find a question on energetics because it hasn't come more recently, but they specifically said that energetics is a broad topic for this year. And so here we are. So a group of students set up experiments 1 and 2 as shown in figure 3. So figure 3, we have our diagram of experiments 1 and 2. So in experiment 1, we have our beaker. It's at 25 degrees C. And as you guys might remember, that is actually standard temperature. So that's standard conditions. It's we have this block of KMnO4, which is potassium permanganate, and it's in 50 centimeters cube of water. That's for experiment 1. And on the right, we have the same setup, except that the temperature at which everything is at is now 50 degrees C. And we have heat being applied under this beaker, but we still have our potassium permanganate block. And again, it's in 50 centimeter cubes of water. So if you think about this from the standpoint of what we typically see when we dissolve potassium permanganate in water, we can say right away that over the 24-hour period, we would see a color change, right? So we would see the entire beaker turning purple as KMnO4 dissolves in the water, right? So we would see that over the 24-hour period, right? How do changes in beaker A differ from that in beaker B? Well, I would say that potentially you would have maybe a deeper purple. So let's just jot that down. Deeper purple present in beaker B at 24 hours due to heat being applied. So more KMnO4 gets dissolved, and we see that manifested as that deeper purple color, right? And I guess I just accounted for those differences by saying that, heat is applied in this case, it's not in this case, and the temperatures are already higher. So more of the KMnO4 will then go into solution at that same, over that same 24-hour period. So you'll see a deeper purple there, right? So let me just jot that down here. So deeper, well, let's say more KMnO4 gets dissolved due to higher temperatures. All right, so that is that. So that's that first part, right? So now let's get into the nitty-gritty, get into this bit on energetics. All right, so now we're at part B. The students conducted a third experiment. So a third experiment now. They did two just now. They're doing a third one now to determine the heat of solution. So let me get my pencil now so I can underline the key terms. Which is I always encourage students to underline the key terms so that when you're ready to work, you can see what the most important pieces of information are, right? So to determine the heat of solution, so this experiment is trying to determine the heat of solution of ammonium nitrate by mixing 8 grams of ammonium nitrate in 50 centimeter cubes of water at room temperature. The temperature before and after the ammonium nitrate was added to the water is given as, so the initial temperature is 27 degrees C and the final temperature is 19 degrees C. So what we can see is that there is a decrease. Right off the bat, we can see there's a decrease in temperature, right? And then now, based off of that, they're asking us whether the process in this experiment is exothermic or endothermic. Now we know that in endothermic reactions, right, these the reactant particles take in energy from the surroundings, right? The reactant particles are taking in energy from the surroundings. So what that means is that the surrounding temperature is going to fall, and that's what we measure in this case. So there's a decrease in temperature. So that means that the system is taking in heat energy. And when it's taking in heat energy, it's called an endothermic process, right? So we know right off the bat that this is an endothermic process. And we know that because we see our temperature decrease, right? So this is the endothermic process. We're good. All right, so let's see here now. Let's see what they're asking over here. Draw a labeled energy profile diagram. Let's move this here. Let's draw a labeled energy profile diagram to show the heat changes involved in experiment 3, right? So what they're asking us to do is draw the energy profile diagram for a process where an endothermic process is taking place. So we're gonna draw our axes. We have our y-axis here and we have our x-axis here. Our y-axis is our energy content. That's what we have on our y-axis, our energy content. And that is in units of kilojoules per mole. And then on the x-axis, that's just our reaction pathway. So reaction pathway, right? So we have to make sure that we label everything properly. Notice I have my units and I have the name of each axis. Okay, now I said we're drawing an endothermic process. So that what that means is that the system is taking in energy. So if we start with our reactants down here, so let me write reactants. We're starting with our reactants down here. And we have the enthalpy of our reactants. That's what this, on this y-axis, that's what this is. So that's reactants, guys. That's what that word is. Enthalpy of our reactants is at this line here. And so what's gonna happen is our products are gonna be up here at a higher enthalpy level. So here are our products. That's an endothermic process. It's taking in energy. Products. So this is our products up here. And so we have our delta H. Of course, our delta H for an endothermic process is positive, as we can see. So then here is our H. This value here will be the H of our products. Products, right? And so at a basic level, this is how you would show the heat changes taken here. They didn't mention anything about activation energy, so we don't necessarily have to show that. But if you had time and you wanted to be an overachiever, you could do that, right? But at a basic level, we're showing our energy content on the y-axis. We're showing our reaction pathway. We have as our reactants down here. We have an increase in enthalpy here. That's net positive as we get to our products because it's taking in energy. And so we see that we have our H reactants here, H products here. So the difference between those two, that delta H is going to be positive as the reaction proceeds. So that's what you're going to, the system is going to take in energy, and that taking in of energy is what causes the surrounding temperature to decrease. So that's how we knew it was endothermic from the jump, okay? So, all right, so now we're good there. So next we're going to calculate the heat change, right? We're going to calculate the heat change when 8 grams of ammonium nitrate is dissolved in 50 centimeter cubed of water, right? So the governing equation, when we start to think about or deal with these energetics on a whole, this heat change that they're asking you to calculate is a Q, right? And so that governing equation is Q is equal to MC delta T, right? So this is the heat change that we're seeking. The mass is the mass of the solution, right? The C is the specific heat capacity of the solution. So that's this, that's right here. And then the delta T is the temperature change that occurred, right? So let's start by calculating our delta T. So our delta T would be equal to our final temperature, which was 19, minus our initial temperature, which was 17, which was our final temperature 19, initial temperature 27. So when you do that math, you realize that what is this number? What is this? What is 20? What is 19 minus 20? So we're going to get a negative temperature change, which signifies a reduction in temperature. So that would be 8, right? So that would be 8 degrees C. Yes, so that's your delta T. So that is 8. Uh, 8 degrees C. And so we know, let's find our mass now. So the mass is the mass of your solute that you're adding. So that's 8 grams. And we can just assume that that has the same density as water. So then that would be essentially 8 cm cubed. That's the same. And then the water, we assume the density of water. So we have 50 cm cubed. This is actually where you apply the density. So we have 50 cm cubed, that's the volume of water, and the density is 1 gram per cm cube. So we can just say that this is roughly 50 grams. So that's actually where you do that, because it's a mass that we're seeking, not volume, right? So we can say this 50 centimeter cube is the same as 50 grams because that's the density of water. And we already knew that this was 8 grams. So we don't necessarily need to do any kind of a thing here, but this is already 8 grams. And we said that this is roughly 50 grams. So the total mass is then 58 grams. That's the mass of the solution. So here we go. So then now we have our mass. So this is our M is equal to 58 grams. Our delta T is this, and of course our C is 4.2 from here, right? So Q is then equal to 8 grams, right? 58 grams times 4.2 times the change in temperature, which is 8 degrees C, and the units of this is kilojoule. Kilo. All right. So here we go now. So the Q is then equal to, let me just multiply that through. So Q is then equal to 58 times 4.2 times 8. So that Q is then equal to, where should I write the Q? I'm going to write the Q here because I ran out of space, right? So just follow me here. Q is equal to 1948, and that is kilojoules. What's the units, guys, of this? That's kilojoules right there, right? The units of mass cancel and units of temperature cancel. So you're gonna get kilojoules. That's your units of heat change, right? So that is your Q. Let me just box this. So that's that. Okay, so that's this. So we're checking off that. So then now state one assumption necessary for your calculation in B part 3 above. There are several assumptions that we make. So let me just write one of them as the question asks, or maybe I'll just write all of them so you guys are aware of them. So one of them is that there's, the most common one I would think is that there's no heat loss to the surroundings. No heat loss to surroundings. So the temperature change that you measure is exactly what it is. None of it seeps out. So there's no heat loss to the surroundings. So that's one assumption right there. And then, so the change in temperature delta T that we measure from here, that's where the assumption comes in, that no heat is lost to the surroundings. What you measure is actually before and after, right? A second one, if you want to take notes on your own, is that the solution that forms as a result of the ammonium nitrate dissolving in water has the same specific heat capacity of water, right? It's not a different specific heat capacity. It's the same as water. And that's why we can use this 4.2 number, because the assumption is that the solution specific heat capacity is the same as the specific heat capacity of the water by itself. So that's a second one. And the third one would be that the density of the dilute solution is the same as water. So the solution that forms that density is the same as the density of water. That's how we're able to use this mass of 58, right? But that's how we're able to add the 8 grams of this to the 50 grams of water, right? So those are 3 assumptions that I gave you right there, but I think the most common one is that there's no heat loss to the surroundings, and that our temperature change is exactly what we measure, right? That nothing is lost. Okay, so here's where the mole concept comes in, right? So from your answer to B part 3, so the answer that we got up here, which was 1948 kilojoules, right? Based on this, you're supposed to calculate the heat change when 1 mole of ammonium nitrate dissolves in water. So, okay, so first of all, we have to find out how many moles of ammonium nitrate this heat change corresponds to. So how we do that, we know the mass of ammonium nitrate that we had. So ammonium nitrate is NH4NO3. And let's just calculate the molar mass for that first. So the molar mass of that is going to be what? It's going to be 14 plus 4 plus 14 again, right? So that's 14 plus 4, right? This 4 from the hydrogen, then 14 again from the nitrogen here, and then we have 3 oxygen, so that's 3 times oxygen is, what is the mass number of oxygen? It's 16, right? So now we do this, so we get 28 plus 4. That's 32. So that's 32 plus 48. So that is 80. Right? So that's 48 plus 32. That gives us 80. So the units of that is 80 grams per mole. That's the molar mass of ammonium nitrate, right? So we started out with 8 grams. So we're putting in 8 grams. We're trying to find out how many moles this corresponds to. So 8 grams corresponds to X mole, given that 80 gram is in 1 mole. How do we solve for X? I know we solve for X. So X is then equal to 8. Let me just work this through the cross multiplications. I think that we did a bunch of this stuff when we did mole concepts, so you guys probably didn't want to see all of this detail, but let's do it anyways, right? So we're solving for X. X is our unknown. So we do our cross multiplication. We do 80 times X is equal to 1 times 8. So when we rearrange, now we're solving for X. X is going to be equal to 8 divided by 80, right? And what's 8 divided by 80? 8 divided by 80 is just 0.1. So X is equal to 0.1 moles, right? So this heat, so here we go now, 0.1 moles results in a heat change of 1948 kilojoules, right? So then if 0.1 mole gives you that, what's 1 mole gonna give you? And you see that they give you it such that you can just multiply, right? You can use some simple factors, right? So 0.1 mole releases this amount of energy. So 1 mole is going to release 10 times as much, right? You just multiply by 10 because it's a factor of 10. That's the difference between these two. So you multiply this by 10 as well. So times it by 10, right? So then X would be equal to 1948 kilojoules. And if we wanted to do it the other way, where we just did the cross multiplication like we just did here, we would say that X is equal to 1948 times the 1 divided by 0.1. So we do that, 1948 divided by 0.1. We get the same thing that we got here, right? So that's that. Let's see what's on the other page. Yep, that's it. So that's the answer to that question. So let me just clear that real quick, and let me just check the chat while I'm at it to see if anybody is asking any questions. And then also let me see if anybody is in the Zoom meeting. Let me see if anybody's on YouTube right now asking anything about this. Yeah, I don't see any questions on YouTube right now. So it seems as though this is all clear to you guys. If you're watching and it's not clear to you, this is your moment. You ask a question about it. Yeah, so this is your moment to ask a question about it. And I was planning on doing another one. But that one involves plots and all that stuff right now. So it would take a little bit more time. Yeah, so maybe I'll just, in the interest of time and so that you guys have time to go back over and do your stuff, I'll just stop here. I'll just end this video here. And then if you have any more specific questions that you wanted to ask, maybe you couldn't just send me a message on Instagram or leave a comment underneath this video. If you're watching this later today, feel free to do that. Because let's see now. Let me go back to my screen here and see. What time is it? 6:30? Yeah, so that didn't take too long. Let's see. So that's what we have so far, guys. Let me just stop sharing this and see something real quick. Mm, 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 mm. Let's see. Yeah, I think I'll just stop there with that. But you can see how you'd work those that out, right? So that's how you go about doing that. So we're just gonna stop here for now. So you guys will have this video as a reference. Really, the key takeaways is how you use the formula. The Q is equal to MC delta T. That's really the crux of it. And then being able or understanding how to make the leap from the value that you get for Q is often just the value for the particular moles of stuff that you are working with. And then often what you have to do at the end is then say, okay, if I dissolved only 8 grams and 8 grams is X amount of moles, and that gave me this amount of heat, then how much will 1 mole give me? Right? And then that's what you do. You just do that cross multiplication and you get your final answer. So beyond this is just, the rest of it is just definitions and knowing what the heater neutralization means, what the heater reaction is, what's the other one, heater solution, and then you should be good to go, okay? So let me know if you have any questions. Feel free to message me on Instagram if you have any more specific questions right now. And then, yeah, all the best in your exam tomorrow. Trust yourself, trust your preparation, and just stay calm and leave nothing blank, okay? All right, so we're gonna end the meeting now, and all the best tomorrow. Bye.